Hey, and welcome back to another LeetCode practice video. I'm going through the backtracking problems on LeetCode.io. This is a curated list of 150 algorithm problems that is an extension of the blind 75 list that contains problems for every different type of technique that's typically asked in coding interviews. So so I've worked my way through these backtracking problems, and I had some challenges with determining the runtime complexity. For those who've watched the previous video, it turns out the permutation is actually O of n factorial time and space. And people write n times n factorial, but if you write out n factorials, it's the same. So it's really just O of n factorial time and space. Anyway, so yeah, the next problem I wanted to tackle is word search. That sounds familiar. I've probably done it before. Let's have a quick look. So yeah, I have solved before. Sorry, here, submissions. Okay, last year, cool. So yeah, let's have a read through it, and then I'll try to solve it, and hopefully I can without knowing the answer in advance, or even remembering the answer. Let's see. So we're given an m by n grid of characters, board, and a string word. We should return true if word exists in the grid. The word can be constructed from letters of sequentially adjacent cells, where adjacent cells are horizontally or vertically neighboring. The same letter cell may not be used more than once. Okay, so this is what the board looks like, and then we can find like a path. We should find probably a path that looks like the word. Let's have a look at the constraints real quick. So this is the board length and height. I'm just going to copy that in here. Okay, so it's guaranteed that we have at least a 1x1 board, and the word has at least one character. We don't care about the upper bounds. Otherwise, our space and time complexity are going to be constant. Cool. So let's read through through these examples. Okay, that's the board. We should match the word A, B, C, C, E, D. And, well, okay, so we do some path finding, A, B, C, C, E, D, and we find it. We're done. We return true. Nice. Second example, we should find the word C. So we have to find the letter S and then start exploring from there to see if we find the complete word as a path in the grid. Next, we have A, B, C, B as an example. So I guess we would start here, match A, B, C, but then there's no B here. Even when we start from any of the other characters, we start at this A, but then we already cut short because there's no B in S and D. Okay, so I think since this is a backtracking problem, what we can do is, well, we'll implement a recursive solution and we'll just iterate over all of the characters as a starting point for our search. And then we call a method that will basically perform a search from that point, and we'll try to find a match. Yeah, that's what we can do. Now I'm thinking about what's in the board. So board and words consist of only lowercase and uppercase English letters, okay? But it doesn't say if oh no, well, characters can be repeated, right? So we see that here. So we could actually, well, if we have a word start with EE, and we could start from this E, go here, go to one of the other characters, or we could start from here, go there, and go over the other characters. And if we're looking for a word that contains maybe, I don't know, 12 times A, and the whole board is full of A's except one B, we will run through all different combinations just not to find a result. So maybe we have to do some optimization to prevent that, but I'm not sure yet. One optimization could be to count the frequencies of the different letters on the board and do a soft match against the letters. Well, we just check if all the letters in the word occur on the board, right? That's something we could do. That would rule out all of the words that don't have where not every character is in the board. Excuse me. Cool. So yeah, I don't like M and N. I like width and height. So I'm just gonna instantiate that. I think I've explained my approach. The approach would be width times height times length of the word time. And in terms of space, we just need to remember which cell we've already visited along our path. So that will be O of length of the word, right? Let me write that down. O of width times height times word length and time, and O of word length space. That's what I predict. Okay, cool. So the width is length of the board, of the first row of the board. That's the width. And the height is the number of rows in the board. So there we go. So yeah, let's define that up here. And then we will, at the very end, we're going to return false if we didn't find a match. And in between, well, in between, we'll have our little helper function, search. We will give it an X and a Y position. And since we're using backtracking, we probably also want to give it an index, an I, that tells us at what position in the board we currently are. And we have to tell it which nodes we've already visited, which we cannot visit again. So search will do its magic here. And outside of the search function, we have to iterate over all of the individual cells in our grid. So for X in, well, or let's do for Y in range height, for X in range width. We're going to if, maybe just to find. If find, we start at the 0 position, X, Y, and visited is going to be an empty set in the beginning. Then we're going to return true. Otherwise, we're going to advance to the next cell. You know? Find word. Maybe let's call it that. Find word. Oh, let's just name it find. I can never make up my mind. But find is fine. That's what I find. Cool. So yeah, so now we have to do something. We have to, well, we have to check whether the position is actually a valid position. If X smaller than 0 or X larger or equal to width, return false. Same for Y. We check if Y is out of bounds by checking if Y is smaller than 0 or Y is larger or equal than the height. Cool. Next, we're going to get, well, the cell value, right? If board at position YX is equal to our word at position I, that's great. That's when we can do the recursion. And we have to start from that point. If that's, if that is a valid position, we're going to have to add this thing to our, well, yeah, let's call this position. We have to add that position to our visited nodes, right? And then we will do the recursive calls. And after we will remove it again. That's what we will do. And maybe we should, I can never make up my mind whether I should make position 2 coordinates or just a tuple. All right. Anyway, I think, yeah, let's leave it like this. Return false. Now, we also have to check, you know, if length, well, if I larger or equal length of the word, return true. That means we found a match. And so if, when we do our recursive calls, what we have to do here, if find, and we have to pass in the next position, nx and y. We have to pass in our visited. We have to pass in index plus 1. And if that is true, we want to return true. That's what we want to do. So, and yeah, in x and y, well, we need to compute that, right? So we want to go up, down, left, or right. So for dx, dy, that's a delta, in zip. And now we need two arrays. So, and then we compute our x plus dx and y plus dy. Now, well, what is the left position? X minus 1, but y stays the same. What is the up position? Well, we don't change x, but we decrease y. And similarly, what is the right position? Well, x plus 1, but y stays the same. And the down position is x stays the same, and y is plus 1. That's what we do. So that iterates now over all of the 4 neighbors. And we should also check. Well, we're not checking if we are in visited, right? And now I'm thinking maybe we should use a tuple just to make that a little simpler. So let's pass in this as a position here, position. And for a little check, we have to say xy equals position, right? But everything else becomes a little easier. And now next position, what does that become? Well, we can just do next position equals that thing. Next position. So there you go. So that's going to be our next position. And we could also just put that in here. X minus 1, x plus 1, x, y minus 1, y plus 1. So next position is really just nx and y. And we change this to next x and next y. We have time to type, right? So let's just do that. X and next y. Cool. So now, but now we kind of have to check if next pos in visited, continue. We're not going to do anything. We're just going to ignore it. Right. So that's what we will do. And here we also have to add it as a position. So we're going to add this as a tuple. Tuple xy, the position. All right. Yes, I think that is everything. So let's try this out with the first example. We start at position 0, 0, right? X, Y, 0. Index is 0. Our set is 0. We're still on the grid, so everything is good. And now we check, is the position at y0, x0, is that equal to the word, first character of word? Yes, it is. Fantastic. So we're adding this position 0, 0 to our visited list. And now we're going to iterate over the left, right, left, top. No, wait, which order did we do? Left, top, right, and bottom neighbors. If we do that, none of these are going to be invisited. So we will actually do the recursion, but then we'll run into this little check here, and we won't do anything for the left and the top one. But for the right one, we actually see, at position x1, y0, it's actually the same. So that means we're going to increase our index again, +1 when we do the next iteration. I think that should be good. So I'm also a little bit impatient. So I kind of just want to test this now. Remember, I'm just practicing. I'm not explaining to you anything. Yeah, so that works. And now I'm curious if my solution will run into a time limit exceeded, which would mean we have to do some optimizations. Wrong answer. Okay, so this is not great. Why do we find a wrong answer here? We returned false. We returned false. Can this happen? So what is this grid? It's all lowercase a's on the top, in the middle all uppercase, and then so A. So we should be able to match this top right corner. Then left edge middle row, all the elements in the bottom row, and then we go up. So it's basically going like a U shape. Small a, large a. 3 A's, large A, small a, large a. So almost like a spiral, right? Okay, so why does this not work? Well, we could do it this. Maybe change this. Just put the check here. We're going to return false if the position has already been visited. You know, I have the suspicion that maybe we terminate too early. We don't go into the recursion one more step to check if this is true. The next position is that. Simplify that as well. Okay. So has that changed anything? We can try, right? So we could just say word is that thing. And our word is this thing. That way I don't have to submit it and, you know, it won't look like I don't know what I'm doing if somebody looks at my LeetCode profile. So I'm gonna run this code again to see if my suspicion was correct. If position in visited, return false. So there's a typo. Invalid syntax. Aha. Because we're missing a closing bracket. Wrong answer. Wait, but now we are returning true. And we were expecting true before, so I think my hunch was correct that we terminate just one step too early. Because it could be, oh yeah, absolutely. Well, we can run into a case where all the neighbors have already been visited and we just match the entire string. But if we do this test now here, that prevents us from going into the next position, even if it's invalid, to check if we matched the complete word. Another way would be to add this test here, right? If thing word, if I is larger or equal to the length of the word, and then return true. We could put that here as well, you know, this bit. But I think it's cleaner that way to have the how do you call this? The end of the recursion condition on the top. So if I run this again, just to check that the test cases pass, they do. Let's submit again. Let's see what we get this time. And it works. Okay, cool. I saw there was a follow-up question here. Follow-up, could you use search pruning to make your solution faster with a larger board? Yes, we certainly could. So we could cache, you know, this recursive call. Well, the first thing that we could try to do is like check, I'm not going to implement this, but check If all of the characters in Word occur in board, that would be the first thing to check. What else could we do? We could also check if the if every character in Word occurs in the board, and if the board contains enough of those characters. What else could we do to prune the search tree? Well, we could remember, when we are in a certain position, we could remember if we try to match the next character from that position and if it works or not. So we could cut short the checking of all the neighbors. We could also, we can basically, we could basically remember, from which position are we able to match as like a substring, stuff like that. So if we, for example, know that from this position where the C is, we cannot match C, C, E, D, because D was something else, that would mean we would never try that position to match that string from that position again. And those positions and those strings to be matched could be substrings that, of the word that we're trying to match as we iterate through the array with different starting positions. And we might still run into that position and blah, 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 blah. So there's some ways of how to do that. I don't see if there's anything in the, it's just blah, blah. Okay, that concludes this problem. Another one ticked off the list, I would say. So thanks very much. And next, let's pick one of the remaining ones.